This lesson deals with supplemental problem 415. You can find this problem in the ECE201 ebook in the Chapter 4 supplemental problems starting on page 17. Suppose that we connect a set of speakers across the outputs of the fader circuit of supplemental problem 4.9. Let's approximate the speaker's resistance as 4 ohms. This would be typical of a car audio system. So we had a left front output and a left rear output. Just put the 4 ohms across that. Suppose I let the music just equal 1 volt. How much power is dissipated in each speaker in each of the 3 pot positions that we selected in supplemental problem 4.9? If we model the pot as we did in Chapter 2, page 49 of lecture notes, then let's plot the power dissipated in each speaker versus rotation using the PSpice program. And lastly, what do the results of B imply about the function of this circuit? First position was fade front, and the output voltage was equal to 0.995 times the input V left. Setting that equal to 1 then, we're going to square that and divide by the 4 ohms and get 247.5 milliwatts. For the left rear speaker, we had a voltage gain of 0, so squaring that, divide by 4, we get 0 watts. So we have all the power going to the left front speaker. Now in the center position, the voltage gain was 0.703 for the left front speaker. Multiply that by an input of 1, square that and divide by 4, and you get 123.6 milliwatts. Same is true though for the left rear speaker because we had the same voltage gain, and for the same input of 1 volt, we'd get 123.6 milliwatts. This is actually half of what we had in this case. So when we're in the fade front position, all the power is going to one speaker, and in the center position, we're putting half for each speaker. So we get equal sound. And this is one of the benefits of how Orban picked the resistor values. Of course, the same thing will happen in the rear position. We had a voltage gain for the left front speaker of 0, so nothing there. And then the left rear speaker had a gain of 0.995. So again, times 1, squaring that, divide by 4. And again, we get the 247.5 milliwatts, all going to the rear speaker. What I want to show you is what happens in between. So let's go back to supplemental problem 314, where we made a variable resistance using PSpice. Now you can only vary one parameter in a simulation, so we have to be a little bit creative how we're going to do this. I want to vary a resistor of alpha times R, that's my pot, and then the other side of the pot is 1 minus alpha times R. But let's multiply that out. So I have R minus alpha times R. So just think of that as a series combination of a positive resistor and a negative resistor. Turns out in Spice, you can actually give resistors negative values, and it'll work with that. I want to vary alpha from 0 to 1. The problem with this is that in Spice, I can't let a resistor equal 0. What I'm going to do is just leave off that 1 point of 0. Here's a schematic of my circuit in supplemental problem 4.9. I numbered all the nodes here, so here's 1, 2, 3, 4, 5, 6, 7, and 8. And I'm modeling my potentiometer as a single resistor here of alpha times 10K, and then a 10K resistor in series with minus alpha times 10K. So it's going to be varying alpha, and I'll be able to get the effect of the pot. Replace the op-amp by its model with a voltage-controlled voltage source. I'll be sensing from the plus to the minus terminal, and then I see a voltage gain of, I would like to put infinity here, times this voltage. I just need to put a big value here. This time I use 10 to the 8th. The same thing for the bottom op-amp. And now I'm ready to encode my circuit with the potentiometer. So below is my Spice file describing my circuit of my left fader. My input is between nodes 1 and 0 and a value of 1. Put some comment lines in here which begin with an asterisk to say that this is the front speaker, and then likewise the rear speaker. So I got my resistor R1 between nodes 1 and 3, a value of 24.3K, the resistor R3 between 3 and 5 and a value of 10K, and R5 between 5 and 7 with a value of 58.3K. My speaker is between nodes 7 and ground and a value of 4 ohms. I'm going to model this pot which is between nodes 3 and 0, but now as a variable resistor. I'm going to call the value of the resistor here alpha, because in Spice I'm going to be multiplying this by R, so I'm kind of playing a little game with the symbols here. I'm going to set alpha equal to 10K, and I'm going to multiply it by a number roughly between 0 and 1, or as close as I can get. My voltage-controlled voltage source is between nodes 7 and ground, and it's sensing from 0 to 5, and I gave it a gain of 10 to the 8th or 100 meg. For my bottom circuit, got the resistor R2 between 1 and 2, see it over here, R4 between 2 and 4, R6 between 4 and 6, and a speaker between 6 and ground. I have a fixed resistor here of 10K between 2 and 8. Then I've got my variable resistor here between 8 and ground, but now I'm going to make this a minus 10K. And again, this program can accept actually negative values even over here. My controlled source is between nodes 6 and 0 and sensing from 0 to 4 with a gain of 10 to the 8th or 100 meg. So now I got to put in dot model. Alpha is the name of my variable resistor and telling it that's a resistor. Basically take this and multiply it by R. I'm going to vary R in small steps so I get 200 data points. If you take 1 minus 0 divided by 200, you get 5 millivolts. I'm going to take 5 millisteps. I can't start at 0 because it would make the resistor 0. I'm going to skip that first data point. So what I'm getting effectively then is multiplying my 10K resistor and minus 10K resistor by R, where R is going from 0.005 to 1. So when I get my graph on the output, it'll be plotting it as a function of R. So here's the output of the left front and left rear speakers. So here's when I fade to the rear. I get most of the signal across that and very little to the front, and then vice versa over here. And you can see that the voltage changes here are somewhat parabolic. What's more revealing is a plot of the power versus rotation. Node voltage 6 was the left rear speaker. I'm going to square that voltage and divide by the 4 ohms. That's actually this plot over here. The left front speaker was node 7, and I'm going to square that voltage and divide by 4, and that's actually this plot over here. It's almost a straight line. I drew a straight line through it. So when the pot's in the center position, I was getting, hand calculation, 123.6 milliwatts to each speaker, and that's exactly what I have here. And then in the extreme positions here, when I fade to the rear, I get nothing in the front speaker, and I get 247.5 milliwatts in the rear speaker. And the opposite occurs at the other end of the pot. I marked a 20% point here. 20% of the rotation, I'm getting 80% of the power to the rear speaker and a little bit less than 20% to the front speaker. Of course, the opposite's happening right over here, where I'm going to get 20% in the rear speaker and 80% in the front speaker. So what I've got here with the orb and pan pot circuit is a variation in power that's linear with the pot rotation. If you turn the pot 3/4 of the way, one speaker gets 3/4 of the power, the other gets 1/4. And this is the advantage of the orb and pan pot circuit and how he picked the resistor values. This is supplemental problem 4.15.